straightforward to represent in terms of inequalities. Z is going to go from 0 to 6 minus 6x minus 3y as we go from the xy plane, from a point in the plane, up to the surface. And then the region is from 0 to 2 minus 2x with respect to y, 0 to 1 with respect to x, just as it was previously. So that we're just integrating 3y with respect to z, then y, then x. Now, we will have a little bit of bookkeeping in the process of doing this integral because we're going to get a y squared over 2 here. So, and I've indicated that result. Factoring out the 3 and the 1/2 that we get from the integration, and then substituting the upper and lower limits, we get this. So we have 6 minus 6x minus 3y quantity squared. Now we've got to integrate with respect to y and then with respect to x. Now I'm not going to go through all the details of that integration. I'll simply say that we can expand this. Just multiply it out carefully, keep track of the details. The worst thing you're going to have to integrate here is a y squared. When you integrate, the worst thing you'll get is a y cubed. So you're going to have maybe a cube of 2 minus 2x when you substitute your limits. And a cube of 2 minus 2x can give you terms up to x cubes. But the integral that you're going to get then after you've done the y integral is just going to be a cubic polynomial in x, and not at all difficult to integrate. Now, quickly, let's suppose what we really wanted was the integral over just the slanted triangular portion of this region. Assuming we've been able to integrate our divergence, which again is very straightforward. It's an easy integral. We can say that the integral over our entire surface of f dot n ds is the integral over S1 of f dot n ds, and I'm not going to write that out, plus the integral over S2, plus the integral over S3, plus the integral over S4. And that's equal to the integral of the divergence of f with respect to the volume. What if what we really wanted to find was the integral over S1, the integral that I've written down here? Because remember, up here, this integral is the integral over the slanted portion, the plane region, between, defined by the 3 vertices. If we know this, if this is known, and it's known once we complete this simple integral, and if these are easy, which they might or not be, might or might not be, then we can evaluate this one. And we can say that the integral over S1 of, let's just put a domino there. Okay, the integral over S1 of f dot n ds would then be equal to the integral over d of the divergence of f dv minus the integral over S2 of f dot n ds minus the integral over S3 of f dot n ds, make that a big S, minus the integral over S4 of f dot n ds. Now, it wouldn't be a bad exercise for you to actually write out what these integrals would be. We've defined S2, S3, and S4. The vector normal to S2 would be what? Negative I. What's normal to this triangle and facing outward from the region? Negative I. Normal to this triangle facing outward, normal vector would be negative j, and on S4 the normal vector would be negative k. Using these normal vectors and writing out something analogous to this, and I guess the other thing is that our ds, since we're just in the plane that contains a triangle, your ds would be dA. For all of these, because nothing makes, well, everything is parallel to the plane in which you're integrating. So it's at least conceivable that this being an easy integral and these probably being pretty simple because of the simple nature of the normal vectors and the surface area increment would be easier than evaluating this. And in many cases, you have a situation where you can do this integral and you can do these integrals, but you have another part of the surface over which you can't do the integral, and you can determine the integral of that open part of the surface.